It sounds like a crazy question. Can we move the Earth? It feels like something from a comic book or a science fiction movie. Our planet is huge. It is unimaginably heavy, and it is moving incredibly fast through space. The idea of changing its path seems impossible, but people have seriously thought about it. Not for tomorrow or even for next century. This is a long-term thought experiment. It is a conversation about the survival of humanity on a timescale that is hard to wrap your head around. The reason anyone even considers this comes down to a simple, unavoidable fact. Our sun is a star. And stars have a life cycle. Our sun is middle-aged right now, it is stable, it provides the light and heat that makes life on Earth possible. But it will not stay this way forever. As the sun burns through its hydrogen fuel, it will get hotter and brighter. This is not a sudden change. It is a slow, gradual process happening over millions of years. But the outcome is certain. In about 500 million to a billion years, the sun will have brightened so much that the Earth will become uninhabitable. The average temperature will rise. The oceans will begin to boil away. Earth will turn into a sterile, scorching, hot version of Venus. After that, things get even worse. In about 5 billion years, the sun will swell up into a red giant. Its outer layers will expand so far that they will likely swallow Mercury, Venus, and maybe even the Earth itself. Our planet would be vaporized. So the problem is not an immediate crisis. It is the ultimate long-term threat. If humanity or whatever we evolve into is still around in a billion years, this planet will have an expiration date. That is the primary motivation for thinking about moving the Earth. We would need to move it further away from the sun, slowly and carefully, to keep it in the habitable zone, that perfect orbital distance where water can remain liquid. But we would have to keep nudging it outward as the sun gets hotter. There is another more immediate reason, though it is less predictable. An asteroid or a comet. We know that large objects hit the Earth from time to time. The dinosaurs were likely wiped out by one. We are tracking many of the big, dangerous asteroids near us, but there is always a chance of one we did not see coming. A large enough impact could end civilization or even all complex life. While we have ideas about how to deflect a single asteroid, the idea of moving the entire planet is the ultimate form of planetary defense. If the Earth simply is not where the asteroid is going to be, then there is no problem. This is a much less likely reason to move the Earth, but it is part of the conversation. So, how would you even begin to do something so enormous? You cannot just attach a giant rocket engine to the South Pole and hit the ignition. The Earth's mass is about 6 sextillion tons. The amount of force needed to move it in any meaningful way is staggering. Any rocket we could build would be like a flea trying to push a freight train. The force would also have to be applied very gently. If you push too hard in one spot, you could crack the planet's crust, causing unimaginable earthquakes and volcanic eruptions. The solution has to be more elegant. It has to use the laws of physics in a clever way. The most talked about method is called a gravity assist or a gravitational slingshot. It is a technique we already use to send probes to the outer planets. When a spacecraft flies close to a planet like Jupiter, it gets a gravitational kick. It uses the planet's orbital energy to speed up and change direction, saving a huge amount of fuel. The idea for moving Earth is to do this in reverse, but on a much grander scale. We would not be moving a small probe. We would be moving a giant asteroid or comet to fly past the Earth. Here's how it would work. First, we would need to find a suitable object, a big asteroid, maybe 100 kilometers across. We would send a mission to it. We would attach engines to it, or use some other method to slightly change its path. We would need to nudge it into a very precise orbit. This orbit would be designed to make it swing by the Earth at a relatively close distance. As the asteroid flies past Earth, its gravity would pull on our planet, just a tiny bit. This pull would transfer a small amount of orbital energy to the Earth. It would be an incredibly small nudge, but it would be a nudge. The Earth's orbit would shift ever so slightly. But there is a problem. When the asteroid pulls on the Earth also pulls on the asteroid. Newton's third law. Every action has an equal and opposite reaction. The flyby would change the asteroid's orbit too, sending it off into a new unhelpful path. Now, we need to use it again and again. So, the clever part of the plan is to use another planet to reset the asteroid. After the asteroid passes Earth, its new trajectory would be set up to send it on a path toward Jupiter or Saturn. As the asteroid swings by the gas giant, it would have another gravity assist. This one would be designed to put it back on a course that will eventually bring it back to Earth for another flyby. In essence, we would be borrowing orbital energy from Jupiter and transferring it, bit by bit, to the Earth, using the asteroid as a delivery truck. We would repeat this process over and over. Each flyby would give Earth another tiny push. One pass would do almost nothing, but over thousands or even millions of flybys, the effect would add up. Over millennia, we could slowly and carefully migrate the Earth's orbit outwards. The scale of this is hard to comprehend. It would be the largest and longest engineering project in human history. It would require a level of patience and long-term planning that our species has never demonstrated. We would have to manage this cosmic ballet for thousands of years, ensuring that each flyby is perfect. And the risks are terrifying. The biggest risk is a miscalculation. We are deliberately steering a mountain-sized rock on a path that brings it close to our home. What if one of our nudges is wrong? What if a solar flare disrupts the electronics on the asteroid's control system? What if a generation of engineers 1,000 years from now makes a mistake? If we got the math wrong, we could accidentally send that 100-kilometer asteroid crashing into the Earth. An impact like that would be an extinction-level event. It would sterilize the entire planet, boiling the oceans and melting the crust. The very tool we are using to save humanity could be the thing that destroys us. The margin for error is 0. Another method that has been proposed is less risky, but perhaps even more technologically demanding. It involves building a giant solar sail. A solar sail is a huge, thin mirror that is pushed by sunlight. The photons from the sun, even though they have no mass, carry momentum. When they bounce off a mirror, they transfer that momentum, creating a tiny but continuous push. Well, we have already tested this technology with small spacecraft. To move the Earth, we could not just put a sail on the planet. Instead, we would need to build a truly enormous structure in space. One idea is to build a massive solar sail, thousands of kilometers wide, and park it near the Earth. This sail would not be attached to the Earth. Instead, it would be a statite, a type of satellite that uses light pressure to hold its position instead of orbiting. We would position this giant sail in such a way that its gravitational pull on the Earth is constant. It would act like a gravitational tugboat, hovering just ahead of our planet and gently pulling it forward in its orbit. The sail would use sunlight to counteract the sun's gravity, allowing it to maintain its position relative to the Earth. Over a very long time, its steady pull would gradually increase the size of Earth's orbit. Another variation of this idea is to build a giant mirror that does not pull the Earth, but pushes it. We could place a huge reflecting lens or mirror in space between the Earth and the sun. This mirror would collect a vast amount of sunlight and focus it into a beam, but instead of aiming the beam at Earth, which would cook us, we would aim it to pass just behind the Earth. The photons in this incredibly powerful beam of light would have their own gravitational field. As this river of light flows past Earth, its gravity, though minuscule, would pull on the planet, nudging it forward in its orbit. The engineering challenges for either of these ideas are immense. We are talking about building structures in space that are the size of countries. Where would we get the materials? Launching them from Earth would be impossible. We would have to mine asteroids and build these megastructures in space. The level of automation and space-based industry required is far beyond anything we can do today. And like the asteroid method, this would take an extremely long time. The force applied is tiny. We would be undertaking a project that would last for millions of years. A third, more brute force method exists, though it is often considered less practical. It is based on the simple principle of a rocket. To move a rocket forward, you throw mass out the back. We could do the same with the Earth. We would need to build a series of massive electromagnetic catapults, also known as mass drivers. These would be huge machines, likely built on mountains, that use powerful magnetic fields to accelerate and launch material into space at incredible speeds. We would essentially be throwing rocks off the planet. We could scoop up material from the Earth's crust and launch it into space. For every ton of rock we throw in one direction, the Earth gets a tiny push in the opposite direction. To move the Earth away from the Sun, we would need to continuously launch trillions of tons of material in the direction of our orbit. This idea has some serious drawbacks. First, we would be literally consuming our own planet to save it. We would be flinging away our own mass piece by piece. Second, the energy requirements would be astronomical. Powering these mass drivers would take more energy than our entire global civilization currently produces, and we would need to sustain that for millennia. The environmental impact would also be catastrophic. Imagine the effect of launching billions of tons of matter through our atmosphere. It would fundamentally change our planet's climate and composition long before we finish the move. Now, what about the debris? We would be creating a massive cloud of high-speed projectiles in our solar system, making space travel near Earth incredibly dangerous. So let's say we solve the engineering. Let's say we choose a method and it works. What happens to the Earth itself during the move? The consequences of altering our planet's orbit are just as complex as the methods for doing it. The Earth is not just a rock floating in space, it is a complex, interconnected system. And it is not alone. It has a partner, the Moon. The Moon is incredibly important. Its gravity creates the tides, which have shaped coastal ecosystems for billions of years. More importantly, the Moon acts as a stabilizer. It keeps the Earth's axial tilt, the 23.5-degree angle of its rotation, remarkably stable. This stability is what gives us our predictable seasons. Without the Moon, the Earth's tilt would wobble chaotically over long periods, swinging from no tilt at all to extreme angles. This would cause wild, catastrophic swings in the climate, with seasons either disappearing or becoming incredibly severe. If we move the Earth, we have to bring the Moon with us. The Earth-Moon are a gravitationally bound system. Any force we apply to the Earth also has to account for the Moon. We cannot just push the Earth and expect the Moon to obediently follow. The precise dance between them would be disturbed. A gentle, steady push on the Earth might slowly pull the Moon along, but it could also alter the Moon's orbit around the Earth. It could cause the Moon to drift further away or closer to us. If we are not careful, we could destabilize its orbit completely, either sending it flying off into space or, in a worst-case scenario, causing it to crash into us. The calculations for moving the Earth-Moon system as a single unit are exponentially more complex than moving the Earth alone. Then there's the issue of the Earth's own rotation. The day is 24 hours long. The year is 365 days long. Moving the Earth's orbit would, by definition, change the length of the year. If we move to an orbit further out, the year will become longer. That might be a simple adjustment for our calendars, but the process of moving the planet could also affect its rotation. If the force is not applied perfectly to the Earth's center of mass, it could introduce a torque. This would act like a hand spinning a basketball, either speeding up or slowing down the Earth's rotation. Changing the length of the day would have massive consequences. It would disrupt the circadian rhythms of every living thing on the planet. It would alter global weather patterns. The Coriolis effect, which drives the rotation of hurricanes and ocean currents, is dependent on the speed of the Earth's rotation. A faster or slower day could completely remap our climate zones. We would be trying to save the planet from being burned, but we might freeze it or subject it to perpetual superstorms in the process. Even if we manage to keep the day the same and the Moon in a stable orbit, the process itself would be perilous. We are talking about a project that takes thousands, if not millions, of years. During that entire time, the planet would be in a state of managed crisis. Every asteroid flyby would have to be perfect. Every bit of thrust from a solar sail would have to be precise. Any deviation, any wobble, any unexpected change could have cascading effects on our climate. The delicate balance that keeps our planet habitable is the result of 4.5 billion years of stability. We would be proposing to intentionally disrupt that balance with the hope that we can create a new one. And beyond all the physics and engineering, there is the human element. A project of this magnitude would require a level of global cooperation and unity that is frankly hard to imagine. Who would be in charge? Who would pay for it? The cost would be incalculable, consuming the entire economic output of the planet for generations. What country or corporation would we trust with the controls of a system that could accidentally destroy the planet? Imagine the politics. One nation might want to speed up the process. Another might want to slow it down. What if a rogue state or a terrorist group tried to seize control of the asteroid nudging technology? It would become the ultimate weapon of mass destruction. The project would have to survive not just technological challenges, but also wars, economic collapses, and the rise and fall of civilizations. How do you maintain a single, coherent engineering plan for 500,000 years? The first people to start the project would never live to see it completed, nor would their children or their great-great-great-great-grandchildren. It would be a project based on a promise to a future that is unimaginably distant. Given these incredible difficulties, it is worth asking if there are better, or at least simpler, alternatives. If the problem is that the sun is getting too hot, maybe we do not need to move the Earth. Maybe we just need to provide some shade. This leads to the idea of a sunshade or a solar shield. The concept is to place a large object in space that blocks a small percentage of the sunlight heading for Earth. We would not need to block much. A reduction of just 1 or 2% would be enough to counteract the sun's gradual warming for a very long time. The best place to put such a shield would be at the L1 Lagrange point. This is a point of gravitational stability located about 1.5 million kilometers from Earth, directly between us and the sun. An object placed there will stay there, orbiting the sun in lockstep with the Earth. We would not have to build a single solid shield. That would be incredibly difficult to build and maintain. A more plausible idea is to create a massive, diffuse cloud of small, independent spacecraft, or even just fine dust. We could send automated factories to an asteroid, mine it for material, and use mass drivers to launch a steady stream of dust or tiny, reflective mirrors toward the L1 point. Over time, these would form a vast translucent cloud that could be managed and adjusted. If we need more cooling, we add more dust. If we need less, we stop adding it and let the solar wind slowly clear the cloud away. This is still a mega engineering project, far beyond our current capabilities, but it is several orders of magnitude easier than moving the entire planet. We are talking about moving millions of tons of material, not sextillions. The risks are also lower. The worst case scenario is not an asteroid impact that sterilizes the planet. It is the shield failing, which would cause a rapid warming event, or perhaps an error that blocks too much sunlight, triggering an ice age. These are terrible outcomes, but they are potentially reversible and probably not extinction level events. A sunshade acts like a global thermostat. The big political question, of course, is who controls the thermostat. There is one final alternative, the one most beloved by science fiction. If your home is no longer safe, you move. Instead of moving the Earth, we could just leave it. We could become a multiplanetary species. The first step would be Mars. We could establish a self-sustaining colony there. Then we could look to the moons of Jupiter and Saturn. We could build giant rotating space habitats known as O'Neill cylinders, which could house millions of people in artificial Earth-like environments. Over millions of years, humanity could spread throughout the solar system and eventually to other stars. We would no longer be a species with all our eggs in one basket. The fate of humanity would no longer be tied to the fate of the Earth. When the sun begins to die, it would be a sad event, the end of our ancestral home, but it would not be the end of us. This path also has its own profound challenges. Moving billions of people off a planet is not feasible. It is more likely that only a small fraction of humanity would ever leave. This raises deep ethical questions. Who gets to go? Is it just a lifeboat for the rich and powerful, leaving everyone else behind to face the end? And is leaving our planet behind a form of surrender? The Earth is not just a rock. It is the world that created us. It is a part of who we are. Abandoning it would be a monumental step. So could we move the Earth? The answer is a qualified yes. The laws of physics seem to permit it. We can imagine technologies and methods that could, in theory, accomplish the task. But the practical reality is that it is an undertaking of almost absurd difficulty. The scale of the engineering, the time scale of the project, the catastrophic risks, and the unprecedented social and political challenges make it one of the most daunting concepts ever conceived. It is not a solution for any problem we face today. Climate change, biodiversity loss, poverty, these are the urgent crises of our time. Spending resources on a plan to move the Earth a billion years from now would be an absurd misallocation of effort. Our priority has to be taking care of the planet we have in the orbit it currently occupies. But as a thought experiment, it is valuable. It forces us to think on a cosmic timescale. It makes us confront the ultimate fragility of our existence. It pushes the boundaries of our imagination and our ambition. The fact that we are a species that can sit here on a small blue planet and have a serious conversation about steering it through the cosmos is, in itself, remarkable. It is a testament to our curiosity and our deep-seated instinct for survival. It is a plan for a future so distant it seems like a fantasy. But every future begins as a thought, a question, an idea. And this is one of the biggest ideas there is.